Welcome back for problem set 25, and this one is pretty entirely on U-substitution, which can be pretty tricky at times. For a good chunk of these, though, they tell us what substitution to make, so it should not be too difficult, at least for these first few. So just jumping right into it, they want us to, they want us to evaluate this integral, making this substitution. So, of course, if I have this integral, and then I say that u is cosine of t, well, then taking the derivative of that, so my du, derivative of u, that's going to be, well, I know it's going to be sine of t, dt, which this is technically implicit differentiation, is kind of what we just did there. And so I can just go back now. I know that u is cosine of t, so this is going to be the integral of negative u to the fourth, right? Times, well, this bit here is all equal to du, so it's just du. So now this is an integral of this with respect to u. We always want to be able to replace that dt with a du and anything else that's left over. We cannot have any extra t's or x's or what have you left over when we do our U-substitution, or else there's really no point in doing it in the first place. But now this is a much easier integral to do, right, than this up here, because now it's just undoing that power rule. So it's going to be adding 1, dividing that, plus c. And boom, that's it. Next up, same kind of thing. We want to evaluate this integral with a u substitution where our u value is that x plus 3 on the inside. So if u equals x plus 3, du is just going to equal 1 dx, right? So that makes it complicated, right? Because just plugging in u and even plugging in that du for that dx, we're still left with this extra x on the outside. So what we can do there is I recognize I can manipulate this a little bit, and I can subtract this 3 off to say that x equals u minus 3. So now I can plug in a u right here, and I can plug in a u minus 3 right here. So it's going to be u minus 3 times, then on the inside it's going to be u to the 7/3, and now I can replace my dx with a du because of that, and then boom. Now this might still look a little bit tricky, but since this is just multiplication right here, I can distribute this out because it's just a single u value. So now, well, this is u to the first times u to the 7/3, so that's, I add 1 to 7/3, which gets me u to the 10/3, and then minus 3 to 7/3, and now again it's just undoing that power rule. It's a lot easier to handle now. So now adding 1 to this, I'm going to get u and then minus that. Then it's 3 times 3/10, which is going to be 9/10, and then plus c. Moving on to number 3. This one's a little different now, but not by much. So we're given this integral, and again, they tell us what U-substitution to make, which is this right here. Taking that derivative, getting du, I'm going to get 15x squared dx, which does help us, except we don't have a 15 anywhere in here. So how can I plug this in for du? Well, I do have an x squared that I need to get rid of, and that this is going to get rid of. I just don't have that 15, so what I can do instead is divide off that 15, and now it's 1/15 times du equals x squared dx, which means I can now replace this bit with 1/15, and then of course that is an e to the u, and then du. Now, that's easy because this is a constant coefficient, and we know the integral of e to the power of anything is just that e to the power of anything, right? So it's going to be 1/15 e to the power of u plus c. And I just realized I left out, no pun intended, an integral part of the questions before, which is where you plug back in that u value at the end. So when I got, what did I get here? I shouldn't have erased my answers. Dang it. Well, in this case, this is our answer for this integral, but u isn't the variable we were working with, so we're going to plug that back in. So our actual answer is now 1/15 e to the 5x cubed, because that's our u value, plus c. Oops, I keep pressing that ruler. Going back up here, let's see, I think it was something along the lines of 3/13 x to the 13/3 plus 9/10 x to the 10/3 plus c. Or I suppose those were u's, actually, sorry. That's what I'd gotten before, but remember that u equals x plus 3, so our actual integral is going to be this plugged in for that u every time we see it, so it's going to be this. As ugly as it is, this is the actual complete correct answer. And then again, don't forget that plus c. And then going back up to number 1, let's see. It was cosine, so that was going to be that's what that was. So that was that, which makes our actual answer that. Okay. Very sorry to have forgotten that. I'm rather tired. My mistake. But now we've gone over that. Let's move on down to number 4. This one, they do not give us what u value we should be substituting with, so we have to figure it out ourselves, which can be very, very tricky. And honestly, sometimes I'm not confident enough. Sometimes you really do just have to kind of use brute force and just try out a few different possible values that you see in there. But from this one, I can see pretty clearly that if I take the derivative of this interior here, well, of course my constant goes away, but this, the derivative of x to the 4/3, is going to be 4/3 x to the 1/3. While we don't have that 4/3 anywhere, we do have an x to the 1/3. And any constants we can just manipulate, right? It's all about getting our variables that we need to get rid of. So that tells me that the interior of this here should probably be our u value. So I'm going to make that our u value. It's going to be that 5 plus x to the 4/3, which makes our du, just like I said, that 4/3 x to the 1/3. Now, I'm just going to divide this off so that we can get that there. So it's going to be 3/4 du equals that x to the 1/3 dx, which now makes our integral. When I go back and I plug things in, I can now plug this in for that x to 1/3. So it's going to be 2 times 3/4. So I'm just going to do 6/4. And of course, there's not a u there. That du we always want to write at the end. But just remembering we've got that du. And then this here is now times u to the 11th. And there goes our du. And actually, I'm going to reduce that 6/4 to be 3/2 because it's just a little easier to work with. Now, taking this integral is pretty easy. Again, we're just undoing that power rule per usual. So that's going to be 3/2 divided by 12, which is then 3/24 or 1/8 u to the 12th. And don't forget our plus c. And we want to plug back in that u value, right? So our actual answer is going to be 1/8. 5, that was a plus sign, 5 x to the 4/3 to the 12th. Let me get that out of my way. plus c. Number 5 is a little different. Looking at this, I see some similar values here, so I'm just going to try out using this interior as my u value. So if I use u equals, I'm just going to rearrange these to be in standard form. Then my du is going to be 14x plus 28, which, isn't quite this over here, but I can see pretty quickly that that can be manipulated into being that, right? Because 14 plus 7x is just the same as this divided by 2. So if I divide both sides by 2, so I get 1/2 du equals this divided by 2, I get that. And now I can plug everything in. So now this is 1/2, integral of, well, I don't want to write that right there. I'm going to write it over here. So now it's the integral of 1/2, because of this part here, times the square root of u du. Remember, I can always write the square root of u as u to the 1/2, and I am going to here, just because just turning it into something I can do, undo that power rule with, rather than memorizing the integral of square root is just easier for me. So now I'm going to add 1, divide by that, and of course we still have that coefficient in front. Those twos cancel, so it becomes 1/3 u to the 3/2 plus c. Again, go ahead and plug in that u value. This time it is pretty long, but that is okay. Right, on to number 6. Number 6 is similar deal, not too bad. I can see pretty clearly that if I take the derivative of that t to the 5th, I get this bit right here. So it looks like it probably makes sense for my u value to be t to the 5th, du to be, of course, 5t to the 4th, which then I just divide that 5 off, so I get 1/5 du equals t to the 4th. So now I can turn that into, oh, and this one's a definite integral, so that's fun. So I turn this into 1/5, and of course that goes away because I'm substituting it in, and it's still a cosine, but now it's a cosine of u du. And of course the integral of cosine is sine, so that's 1/5 sine of u on these bounds. And we should probably plug back in that t value. There's a special thing you can do here is, of course, we're not evaluating on these bounds anymore because those bounds are for when it is a t value. What we're really evaluating it on is we want to be careful actually to write this part out, or else we're technically writing it incorrectly. Because if I just left it as 2 and 0, that's implying that those values are the u values of 2 and 0, which of course if we plug that into this, don't work. We're going to get a very different answer from what the correct answer is. We could of course adjust these bounds to be in terms of u. So obviously if I plug in that there, that's still going to be a value of 0 for u. But if I plug this in, well, it's going to be 2 to the 5th. So if I was to just leave it without that t equals, it would actually need to be that for us to evaluate it with just the u, which we can do. We can do this where we don't even have to plug this back in, and I can evaluate it with that inside there. But I think it's just better habit to substitute back in, just because not doing so leaves a lot more room for error, in my opinion. So again, be specific. And now if we plug back in that t to the 5th, so that's 1/5 sine of t to the 5th. Now it's 2 and 0. So now let's see. That's 1/5 sine of 32 minus 1/5 sine of 0, which is just 0. So then this is our answer. And you see how that would be the exact same if I had a u value of 32 and a u value of 0. For that, I would have gotten the exact same answer because we're adjusting for that. But again, I just want us to be very careful there. But so this is our answer. Now I've just got 2 questions left. Number 7 isn't too bad. Number 8, however, is particularly tricky. So forgive me if I stumble a little bit along the way with that one. But number 7, of course, comes first. So looking at this, I know that I noticed that I've got this exponent here, which tells me I should probably want my u value to be this right in here. And just double checking, I know, of course, if I take the derivative of a cosine, I'm going to get negative sign, so that looks like that checks out. So if I set u equal to cosine of x, that makes du equal to negative sine of x, which then makes my integral, sorry, I was just giving a little lecture on how I need to be more specific with this, and I always forget to do it myself, which is part of why I recognize how important it is, because I've gotten points off on it in high school before. But then, let's see. So now I'm going to plug that in. So that just turns into a 1 up there, because that's going away. And now it's u to the 6th du, which of course is just us undoing that power rule again, because that is the same as this. So undoing that, of course, is then going to be this, or I could rewrite it this way. And then of course there's going to be a plus c, but because we are evaluating a definite integral, we don't really need to do that. So it's going to be this, and I'm going to go ahead and plug that cosine back in. Okay, and then plug in that upper bound. Cosine of 0 is 1. That to the power 5 is 1. Times 5 is 5, so that's negative 1/5. Minus now, cosine of pi over 4 is square root of 2 over 2. Yep. So then that's going to be this to the 5th, which gets a little ugly. I really don't want to do that. Honestly, I know it's whatever this to the 5th over 32 is, and then this bit times 5 because of that, and then that's all negative, so it turns into a plus sign. Okay. And that's pretty ugly, but I do think that that is our answer. Oh, actually, this here, I see that my lower value, my lesser value, is up at the top. It's that top bound there. So that's what's the actual term? It's like an irregular integral. Improper integral, I believe, is the correct term here. So we would want to flip this, which would end up making this negative. So I think that this would be our answer, but it would have a negative in front. So this is this one here is where I would typically I would just plug in the calculator to put that in. And now finally, number 8, which is not my favorite, because this one is tricky. Obviously, looking at it straightforward, if I make my u value that x to the power of 3, that makes du an x squared. But it's an x squared dx, and my dx is not inside of here, but it's on the outside of all of it. So that doesn't end up working. But of course, if I then have maybe that x squared, or that x squared minus 6 is my u value, then my du value only gets to be an x, which I can't have, say, du cubed. That's not something we can do. So this doesn't work either. So we're left kind of at a tricky spot where it's pretty difficult to figure out what to do next. But we can try making this whole term that u value, and it's still going to be pretty confusing, pretty tough to go from there. but we're going to try it. And I'm going to turn that into that 1/2 power, because it is the same thing. It's just a little bit easier to work with when it's in that power form there. And then du, of course, is going to be, we need chain rule, so it's going to be 1/2 times 2x, so it's just x, then times the inside, and then subtract 1 from the exponent. And that's not super helpful for us. Struggling to remember how I went about this. I know, I'm pretty sure that this is the right track. Then from here, I could undo this square root. So I could multiply, I could square both sides of this. So I'm going to get u squared equals then this right here, which then means if I, of course, add 6 to both sides, so I get u squared plus 6 equals x squared. How is that helpful? This is a very tricky problem, and it had me stumped for a little bit, and I'm now struggling to remember how I figured it out. Let me see if I can locate my previous work for it to jog my memory. Oh, right. That was something I'd forgotten about. I see it now. The light at the end of the tunnel. So then I can have a du times u is going to equal this times this, and because this is the same as this, but this is to a negative exponent, that means this is going to be on top of this as a fraction, so those cancel out. And I just get that, and if that's a little unclear, it's of course this times that x, and then times this, since this is a negative exponent, I can rewrite it down here. And of course those cancel out, which is how I just got that x. From there, it's still pretty tricky. And I don't remember how that's, yes I do, because we just found that this equals x squared. So then if I have an x squared times an x, that's going to get me that x cubed that we want to get rid of. So then I can have u squared plus 6 times u times du is going to equal x squared times x, or that x cubed. Now we have a u value, which takes out that, and we have, well, this, which takes out that x cubed. And now, as convoluted as that was, we can plug it all back in. So that's going to be integral. We've got this u value, so it's u times all of this times u squared plus 6 du. And of course we can combine like terms there, so it's going to be u squared plus 6, and then distribute that. It's going to be u to the 4th plus 6u squared du. And now, once again, we're just undoing that power rule. So we're going to get then this plus this, and then 6 divided by 3 is of course 2 plus c. Now I plug back in that u value, as annoyingly or frustratingly large as it is. So it's going to be x squared minus 6 to the 1/2 to the 5th, so to the 5/2 over 5, plus 2 x squared minus 6 to the 1/2 to the power 3, plus c. And I really hate that problem, but we did it. And hopefully hopefully that made sense. I remember when I was initially doing this problem, it was a good little bit of trial and error and just kind of playing around until I found things that worked. Because a lot of recognizing what U-value, what we need to do for that, and like what we need to make our U-value, and then how to substitute and kind of rework those values there, is a lot of pattern recognition, which isn't always the easiest, and definitely comes with practice. But I hope that question made sense. I hope that all of these made sense, and I hope that this video was helpful. Again, thank you for watching.